Hello and welcome back to Calculus 3, section 13.2, double integrals over general regions. Wow, all right. Settle down. It's 3,000 people in the classroom, obviously. Very excited about double integrals. So we already talked about rectangular region, which when we say rectangular region or we say general region, it all is talking about the domain on which we build up our function. So why is this color? So 13.1, rectangular region, was some kind of a rectangle in your XY domain, and then the shape was built above it, and we had A and B on the x-axis and C and D on the y-axis, and we said that double integral over region R for f of xy dA was representing a volume, because two integrals gave us the area and then the function is the third dimension to give us volume. So this was a volume integral, and it was computed either as fxy dx dy, or it was computed as fxy dy dx. And we had over here C, D, A, B on the inner one because x is the inner, and over here we have A, B, C, D because x is the outer. So that was 13.1. How is 13.2 different? Well, 13.2 now has general region. And if you have a general region, then your domain is going to have two functions. There is going to be a function g of x and function h of x. And these are just your regular pre-calculus 1 functions: linear, quadratic, cubic, trig, exponential, logarithmic, whatever, right? And as you can see, they create this region because they are going to intersect and create the region. And now our shapes, instead of having a rectangular stencil, right, the cookie cutter thing, instead of being rectangular, is going to take the shape of whatever we get as a shape when we intersect objects. So now you can see that you have functions x, well, of y in respect to x. So that's what the general region is. And then you build the shape above that general region. So you have this shape, right? And that's not a rectangle in a base. Therefore, this is not an object that we will use the rectangular integral for, because the domain, right, on which it sits, domain is not rectangular. And we can find other objects. If you take a look at this mouse, right, computer mouse, that's not a rectangle, it's round. So we can actually figure out what these functions are and then have that, and then whatever the surface over here of the mouse, that's going to be given by f of xy, and we can compute the exact volume of this mouse by having the domain to be described by the functions that trace the base of the mouse, and then have whatever function xy governs the top of the mouse to give you the volume in this double integral. But then again, some other things like this computer charger here, it's just a brick, right? So this would be a rectangular domain because it's a rectangle in a base and it's a box. Obviously, you should be figuring out the volume x times y times z from your middle school. But you can also do calculus, right? So we have all types of different bases for our objects, and that base is either rectangular, we use rectangular domain, or it's intersection of these functions, or circular, we're going to use polar. That's 33. I just spoiled it, right? Didn't I? The preview, whatever, right? It's just to get as soon as possible to bed and pass out, right? How many of you have linear tomorrow? So those are the ones who left, because they have an okay. So general region. So what am I going to have for the general region? Well, looking at this picture, the double integral over the general region R of f of x, y, dA is going to be given by the double integral f of x, y, dy dx. X goes from A to B. So looking at this picture, the intersection point gives me A, and another intersection point gives me B on x-axis. So A to B for dx, which is the outer integral. The inner integral is the dy integral, right? And that one has to go from g of x to h of x. So now we have functions in limits, not just numbers. Previous section had 4 numbers in limits. Now we have 2 numbers and 2 functions. So this is the way we set up these guys. Now, in my humble opinion, it is very simple to understand this formula and see this formula if you draw dx. We know that the dx is supposed to travel or take on all positions from A to B. So that's dx position. And now what would the dy? dy position will be from here to there, which is 0 in this case, becomes larger and larger and larger, and then smaller and smaller and smaller and smaller, and then goes back to 0. So the motion this way, right, from A to B, is the outer integral dx, and then its ever-changing height is the dy, and that happens between these 2 functions. Whatever way you want to reason with this, but you know, as soon as I draw dx, it's clear that this actually works. Again, this fxy in the middle has nothing to do with anything. This is just, if you take it out, you will just be computing the area over here. If you put it back in, that means that there's some kind of surface on top of it, some kind of shape, and that shape is governed by whatever this is. So, if you have a rectangular region, right, then A, B, C, D. If you have general regions, then those are some functions, and your dx is stuck between, right, those functions. So, vertically stuck, right? Horizontally, it swipes from A to B. So let's take a look at an example of this. If this ever loads. Maybe I should immediately write the other one as well, since it's going to take its sweet time to load. You can have C and D over here, because now we're doing dx dy. And if you are doing the dx dy, these are not interchangeable. So this is going to be some function g of y, and it's going to be some function h of y. I'll just put, it is not trivial to change the order of integration. And I will write in parentheses that dx dy is not the same as dy dx for general regions. It is the same for rectangular region. I know I made sure you hear it a number of times. So they are the same for rectangular region. All you do is you swap the integrals and you use the appropriate limits. But now you can't do that. You cannot swap two, and I'll show why. But let's do some examples first, and then we'll also see that we can't swap these easily. So first example is for us to just compute the double integral with functions inside the limits, and then we are going to work on the next level up, which is setting up these given some kind of applied setting, and then as most challenging part, to swap the order of integration. So let's do the basic thing first, and that basic thing could be, let's go with the problem 20. This is just a quick practice. So problem 20 says compute 0 to 3, x squared to x plus 6. We are computing x minus 1 dy dx. We know how to compute this. We just integrate the inner integral first in respect to y and use the limits. So when I integrate this, 0 to 3 integral gets copied because I'm not doing that one yet. The integral in respect to y is going to be x minus 1 is a constant, and when we just pick up y, and that's going to be computed between x squared and x plus 6, and we still have dx for the first integral. So now integral 0 to 3, we are going to have x minus 1 times, and now you have upper limit, which is x plus 6, minus the lower limit, which is x squared, and everything's dx. So now we distribute and then integrate. This is a Calc 1 integral now because we did the inner one. So we have integral 0 to 3, and now we have to FOIL all of this. So what do I get? I get x squared plus 6x minus x cubed minus x minus 6 plus x squared dx, and then we put this together. So negative x cubed plus 2x squared plus 5x minus 6 dx. And now just do the calculus 1 integral. So that's negative x to the 4 over 4 plus 2/3 x cubed plus 5/2 x squared minus 6x computed from 0 to 3. Since it's a polynomial, we don't have to worry about 0 because 0 will kill every single term over here. We just worry about 3. 3 to the 4th power is clearly 81. So negative 81 over 4 plus 27 times 2 is 54 over 3. And then one of those will cancel. Plus 3 squared is 9. Times 5 is 45 over 2. And then minus 18. So 54 and 3, I should have canceled that earlier, so that's 9 times 2, so that's 18. I'm just going to call this 18 over here. And then 18 minus 18 cancel, which is great. I have negative 81 plus 90 over 4, and I have 9/4. So the volume inside is 9/4. Now we can draw the domain and understand the domain of this function. That, right, the shape of the stencil. That's what we are doing. So what do I have? I'll put this as let's do it green. It's just a practice here. Understand the region R, which is given through the double integral 0 to 3 x squared to x plus 6. I think that's the, yeah. All right. So this is what is given to us. All I need to do is to draw this. It's x squared. So let's draw. X plus 6. It has the origin, then we go to the 6 up. I have to put this down more. So this is where the 6 is. And then we are going to draw the 45-degree line that goes on forever. And this is my x plus 6 function. Now I need to draw x squared function. Well, we have 0, 0, 1 and 1, 2 and 4, and then on the negative side, as you can see, and then 3 and 9. So 3, 4, 5, 6, 7, 8, 9, and 9. And now we draw a parabola through this. So now, what is the region that they want us to consider? Well, we use the function part. We use the function part to draw the functions, and then we use the numbers over here to cut off everything we don't need. So it needs to go from 0 to 3. 0 to 3 is right here. So everything that is in my box, from 0 to 3. So this is the region. This is what the stencil is going to cut in a cookie dough. It's going to cut shapes like this. So what you are looking at here is the base of the object. The object is coming out at you. This is the floor, right? The XY plane is the floor. So the base of your object will have this shape, and then the walls of the object will rise straight up, and then the top will be curved in whatever way f of xy curves. So that's what we have now. Now, I also mentioned that it is not straightforward. It is not easy to change the order. Our problem was dx, the dy dx. Please note that if you just simply swap this, you will get the most ridiculous thing that does nothing. If you swap these two, get dx, dy, and you simply swap their limits, you see that what you have there is total garbage. It's garbage because when you compute the inner integral, and that's the one you have to compute first, if you compute the inner integral, your answer would be a number, say 10. And then you will integrate that 10 in respect to y, and you will get 10y. And then look at your limits. Are you going to get 9/5 or whatever it is? Hell no, right? So you cannot simply swap limits. It doesn't work, right? We have to actually do a lot of stuff. And you will see that doing the green thing over here is just a part of it to swap the limits. So for rectangular regions, you are welcome to swap the order of integration and just swap the numbers on integrals, and you're good to go. For general regions, no. You have to go through procedures and things to do that. Let's see what they have here. Here's the beautiful problem 28. It says, compute the double integral of x plus y dA. They're leaving it open to us to have either dy dx or dx dy, depending on the rest of the problem. Where R is the region in a first quadrant, bounded by and now we have x equals 0, y equal x squared, and y equal 8 minus x squared. Forget about setting this up without a picture. It's not gonna be good. We have to draw this. Oh, now it's 8. Great. So we go 1, 2, 3, 4, 5, 6, 7. That's 8. So this one over here is 8 minus x squared. We know that 8 is the y-intercept, and then minus x squared opens downwards. Now we have the other function x squared. That's the one that it's easy from before. Oh, nice. And now they said x equals 0. Well, x equals 0, that's the y-axis. And I hope you guys see that this is the region. This is region R. The next question here, and you will really need to re-listen this few times, what I'm going to talk about now. So mark the time on the video and then go back to it. I need to pick between dx dy or dy dx, and the way to pick is dependent on the functions that you are given and the picture, right, what they look like. So I know the form. It's numbers, it's functions, right? And I have the functions y equal in terms of x. If I have functions y equals in terms of x, well, that means that these functions over here act as y1 and y2, which is great, because what do I know for my limits? It's x1, x2. Actually, let me give the assignments. So with these guys and these guys, there we go. So on this one, see, dy is on the outside, so I'll have c and d over here, and then the functions in terms of y on the inside. So g of y and h of y. For these guys over here, x is on the outside, so this is a and b, and over here we have g of x and h of x. So there are many different ways in which you can reason whether you need dx dy or dy dx. One of those is now, well, the functions that are given to me are both in terms of x, and this one has functions in terms of x, or the other one has functions in terms of y. That's one of the ways, maybe the most obvious one. But there are much better ways to understand this, and probably the best one is obviously to draw representative rectangle. If I draw dx representative rectangle, I can see that it swipes from 0 to 3. 3 is the, sorry, from 0 to 2. 2 is the most right that it can go. So the first one, the first infinitely of the other ones, right, positions from 0, and then at x equals to 2, we cannot go past that point. At x equals to 2, the height of our representative rectangle is 0, because the two functions intersect there. So I'm eliminating this one for few reasons, right? First, my functions are not in terms of y, and also I see that dx works just fine. Swiping from left to right, top of the rectangle always swipes one function, and the bottom also swipes one but different function. Be careful, if you have a situation like this and you put dx there, well, clearly it's wrong, because the top of the rectangle is touching whatever the function is, and the bottom is touching the same function. So when you subtract those two, you get 0. So method fails there. So you can't do that, right? But in our case, we can. So I am setting up a double integral of x plus y. And now we know we need to use dy dx. We know that it's 0 to 2 on the outer integral, because the representative rectangle is going to start at 0 x equals 0, which is y-axis, and swipe through the shaded region all the way to x equals 2 and stop, because it can't go past that point. Now the integral, the limits inside, the top of the rectangle is touching the 8 minus x squared, and the bottom of the rectangle is touching x squared. So now we are going to integrate this. We are integrating in respect to y, so I'm having xy plus y squared over 2, computed from x squared to 8 minus x squared, and I still have dx, because I haven't done that integral yet. Copy 0 to 2, integral. And now inside the parentheses, plug in the upper limit. So that's going to be x times 8 minus x squared plus 1/2 8 minus x squared squared. And now the bottom, so minus x cubed, because you have x times, right, and then x squared. And then we have another minus 1/2, that's going to be x to the 4th, because, right, we have y squared over here, plug in x squared inside, get x squared squared, which is x to the 4th. Now simplify all this mess so that we can do Calc 1 integral. I have 8x minus x cubed plus, and now I need to FOIL this. Well, 8 squared is 64, and half of that is 32, minus 8 times 2 is 16, but half is 8, so 8x squared, and then plus x squared squared is x to the 4th, so 1/2 x to the 4th, minus x cubed minus 1/2 x to the 4th dx. Well, these x to the 4ths cancel, at least that much. How my cubes? Negative 2 x cubed. Where are my squares? Minus 8x squared, single x's, plus 8x, and then constants plus 32 dx. Integrate, and we're done. So what do I have here? I have, when I integrate, it's going to be over 4, so it's negative x to the 4 over 2, because cancels, minus 8/3 x cubed, can't do anything there, plus 4x squared, I can do that, plus 32x, computed from 0 to 2. So I have negative 8 minus 64 over 3 plus 16 plus 64. We do not have to worry about 0 now because it's a polynomial. So what do I have? 16 minus 8 is 8, plus 64 is 72. Right? And then minus 64 over 3. Common denominator is 3. 216. Minus 64. That gives us what? 152 over 3. 1 plus 5 is 6, plus 2 is 8, not divisible by 3, so 152 by 3. Anyone? Whatever, right? Good? Multiple ways to see it. One way is to understand that once you know the formula, you will see that these guys, the limits, are in terms of x, and these two functions are given in terms of x. That's one way. Another way is to see over here when I draw the representative rectangle, right? In Calc 1 you have representative rectangle swipe across from A to B. Now you see that over here A and B, right? So the representative rectangle would swipe, and that means that the dx is the main for the problem. Now we'll try. No, we'll try. I want to find another problem that we can solve where we have something else. Let me find more problems. All right, let's do problem 38 and address more this situation. So problem, say 38. It says that the region is in the first quadrant bounded by, so they don't give us f of xy. This means that f of xy is 1, and we're technically just looking for the area. The region in the first quadrant bounded by the x-axis, so first I put problem 38. R is bounded by, they say x-axis. Well, that's y equals 0, right? It's bounded by x equals 6 minus y, and y equal root x. I'm not even going to think about this problem until I have the picture for it. So what do I have? I have this linear line that it's given in a weird way, right? We're not used to having y there. So what I'm going to do here is I'm going to write y equals to negative x plus 6. This is what we are used to. I need more room. So what do we have? Again, linear line at 6 y-intercept, so that's here. We are going to go 45 degrees down. 9 and 3. So this is the function axis, and these. What do I shade? This one, right? No, very good. No, no. 4 of you were going, no, 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 no. That's perfect. This one. And that could be, well, you know, one of the tricky things for some of you to get. This is the region R. Because this region has all of the features. It is touching the square root function, it is touching the linear line, and it's touching the x-axis, right? This one over here is touching the y-axis. This one over here is not bounded on the right. It goes forever. That's infinity. So you only have two regions that are bounded. But then this one is touching the x-axis, as the problem wants, and this one is touching the y-axis. So you have to be very careful, right? And if you're not drawing these functions, the domain, x, y, good luck with setting up anything. You really have to be able to sketch these things. And now we are getting again into the question dy dx or dx dy. Well, if I'm going to use the one that we pretty much always used, which is dy dx, that means that dx is the main integral, and I need to draw representative dx. Now we see that for dx it's going to be easy, right? Because the limits are 0 to 6. That's not a problem. But look what's happening on the top of that representative rectangle. It is going to follow the square root function, and then at 4, it's going to follow the linear function. And that's not good. I mean, you can still solve it, but you need two integrals. First integral, right, you would have to cut right there. And you would have to write one integral from 0 to 4, one double integral from 0 to 4, and then another double integral from 4 to 6. So it seems that having a dx integral is not a good idea. How about dy? So that dy is the main one. I still have my limits for the outer, which should be the numbers. And I can get that simply from 0 to elevation 2. So that's good. I still can satisfy dy integral. But now look at the dx part, which is how big this one is. You have this side for the top, and you have this side for the bottom. So when this dy rectangle starts, it starts on the bottom. It's maximum stretch, right? And then as it takes on all of the values from 0 to 2, it's getting smaller and smaller and smaller and smaller and smaller and collapses into 0 right there. So both of these work just fine if I use this order. If I use that order, I can deal with dx, I can't deal with this one. So that's why, right, it's not easy. You have to have multiple integrals. In some cases, you won't be able to do it at all. In this case, at least, because these functions are, you can flip them easy, right? You can use whatever you want, just one or two integrals. But in some cases, you are not able to flip the function, and that is the issue. Or you flip the function and you get some, I don't know, thing that you can't integrate. Yeah, good luck with that as well. So we picked this one because we can do one integral. So what is that one integral? It's double integral. I'm going to put 1 dx dy. They never gave us any function for the top. So I'll just put 1, and we're looking for area. Now, what are my limits? I already said 0 to 2. That's your C and D. And now, the one that it's far to the right goes on top, and then the one on the left goes on the bottom. But they have to be functions of y. Well, that's good, because the top one was already given to us as 6 minus y, so yeah. The problem is that the bottom one was given as y equal x squared. Sorry, square root of x. Square root of x. So how do I write this in terms of y? I square both sides, right? So y equal root x Square both sides, you get y squared is equal to x. Yay, that's a y squared right there. It's going to take some time to get through all of these things. So now we solve the inner integral first. We are integrating in respect to x. Well, it's easy because integral of 1 is just x. And we are computing from y squared to 6 minus y. We still have dy to deal with it. 0 to 2. Upper limit is 6 minus y, minus the lower limit is y squared. Note my use of parentheses. Now integrate in respect to y is a 6y minus 1/2 y squared minus 1/3 y cubed from 0 to 2. Again, we are not going to worry about 0 because we have a polynomial. So I have 12 minus half of 4 is 2 minus 8/3. So that's 10, 30, 22 over 3. 23 over 3. We'll have to continue this next class since you want to go home. I have at least another 3 examples, including change of order of integration. So we'll do more next time on Wednesday. See you then.